So I'm going to study insurance arrangements in a world where agents face Knightian uncertainty. By Knightian uncertainty, I mean environments where agents entertain more than one probability specifications for the randomness they face. In these environments, there is a unique feedback between risk sharing and risk perceptions. And this feedback is going to affect how efficient risk sharing schemes look. The source of this feedback comes from how the attitude towards ambiguity or model uncertainty is characterized. Typically, there is a prior selection rule which maps endogenous outcomes to particular choices of probability assessments. In a setting where you have more than one agent, these endogenous outcomes are going to come from risk-sharing arrangements. And so we can see one part of the link where there is a link from how risk is shared to how risk is perceived. And given these perceptions, agents will have demand for insurance, which is going to affect how actually the risk is settled. So the efficient risk sharing schemes are going to internalize this feedback and eventually shape the ultimate shape of the risk sharing arrangement would come from both these features. These settings also allow us to think about endogenous heterogeneity in beliefs. So this point was also brought up in the earlier presentation. And what could happen here is that if the outcomes are different for different agents, the prior selection rule is going to work differently for both of them, which means that the worst case models would be different, and that could be interpreted as endogenous heterogeneity in beliefs. So I'm going to have two sources of non-diversifiable risks, aggregate risks, and uninsurable idiosyncratic risks from informational frictions. So my benchmark will always be the von Neumann expected utility framework. And as a point of departure, I want to highlight two results in this benchmark where efficient allocations are consistent with long-run emissarization of agents. And by long-run emissarization, I mean that a subset of the consumption of subset of agent goes to 0. So the first setting is asymmetric priors and symmetric information. This was studied in Bloom and Easley. And they basically explained Friedman's market selection hypothesis, where if agents have asymmetric priors and these are exogenously different, some agents are closer to the data generating process than the other. And eventually, the insurance arrangement makes, or the guys who are farther from the data generating process lose out on insurance arrangements, and their consumption eventually goes to 0. The other setting is a setting where you have symmetric priors but asymmetric information, a version of which was studied in Atkinson and Lucas. Now, in these settings, there is an interaction between incentives and insurance. The insight in Atkinson and Lucas was that to provide efficient insurance, you need to vary continuation values, or you need to use smoothing across states and across times. And this smoothing across time would eventually lead consumption to span out, and a subset of agents, the cross-sectional inequality in consumption, to become arbitrarily large, or a small section of or subset of the agent's consumption going to 0. So the link between these two results is that both of them are properties of efficient allocations. And I'm going to argue that this feature of endogenous heterogeneity in beliefs will generate survival forces in both cases. And we'll see how. So the setup is simple. I'm going to study an exchange economy with two agents. And there are going to be two shocks, one to the size of the aggregate endowment, and one to the split of the aggregate endowment between these two agents. Both of these shocks are going to take two values, high and low. So in particular, agent 1's income would be y times s, and the rest of the aggregate endowment goes to agent 2. The preferences I'm going to use are a version of the recursive multiplier preferences. So at least for the rest of the talk, we can focus on the case where the approximating models which the agents have is an IID model across time. So the value of a consumption process, which is measurable to the shock z, is given by this recursion. So this recursion is standard, except that there is a T operator instead of a conditional expectations operator. So what is this T operator doing? This T operator is taking conditional expectations with alternative probabilities, and these alternative probabilities are absolutely continuous with agent I's approximating model. Now this is a huge class of alternate probabilities. To discipline the search, we add on a penalty which scales up with entropy. So the minimum of this conditional expectation is what the operator T returns, and that is what appears instead of the conditional expectations operator. So in particular, as theta goes to infinity, we'll approach expected utility since the cost is so high, the agent is going to settle down on his approximating model. And as theta goes to 0, he's basically going to entertain a lot of a huge class of alternative models. Now suppose that U is concave, satisfies the inner condition, and U0 is well defined. So what are the sources of what are the potential sources of heterogeneity in this setup? First of all, agents have asymmetric endowments, since the allocative shock could be high or low. If the relative entropy of their approximating models or the reference models is greater than 0, we denote that case as a case when agents have asymmetric priors. And when S is private information, we'll denote that case as asymmetric information. So let us start with the first case where there is symmetric information but asymmetric priors. The efficient allocations in this setup can be written as a Planner's problem, or can be written as a solution of a Planner's problem. And this Planner's problem can be written recursively in the following way. So we have two agents. Let V be the promised let V be the promised value for agent 2, and Q be the maximum value which can be given to agent 1, subject to the fact that this promise is kept by the planner. So what the planner is choosing is consumption today and a menu of continuation values tomorrow, such that he satisfies the resource constraint, and the choice of consumption and the continuation values actually keeps the promise. And there are natural bounds for the choice of this continuation value, which comes from the fact that U0 is well defined. This is just the value associated to agent 2 with 0 consumption, and the value associated to agent 2 with consuming the entire aggregate endowment. So it's instructive to stare at the first order conditions for this Planner's problem. So the first order condition says, so lambda is the Lagrange multiplier of the promise keeping constraint. And this can be, in a way, interpreted as the implied Pareto weight on agent 2. So the first condition, which is a standard condition, says that while choosing consumption, the planner is going to equate the marginal utility of consumption for agent 1 to lambda times marginal utility of consumption to agent 2. And the second equation says that the value of the Lagrange multiplier tomorrow, weighted by the relative likelihood of the shocks tomorrow, is equalized across states. And these likelihoods across agents are computed with their respective worst case models, which is the solution to the T operator which I introduced earlier. So one thing to note from this slide is the following. Suppose you had a world where agents had, or you had a setting where you had exogenous heterogeneity in beliefs. You would have the same first order conditions. But now we have a restriction on where this heterogeneity comes from. It has to be such that given the heterogeneity, the outcomes in the economy are consistent with the beliefs which would be implied by these restrictions. So any outcome in this economy can be split into two parts. First, assume that agents have heterogeneous beliefs, figure out what the allocations are, and then check whether this belief heterogeneity is consistent with the allocations which you get. And the fixed point of this loop will ultimately shape how the consumption allocations or how the aggregate risk in this case is shared. So in this setting, there are two belief selection processes which are going on. On one hand, the market weeds out incorrect beliefs because you have agents with potentially asymmetric priors. But agents are also dealing with multiple priors themselves, which depends on their wealth. So the essential heterogeneity in the beliefs has a component which is endogenous and has a component which is exogenous. So with this setting, we can ask what happens to Friedman's market selection hypothesis. So let P0 be the data generating process. So I'm not going to take a particular stand on what it is now, but it could be arbitrary. The planar solution gives us that the growth rate of the Lagrange multiplier, the one period ahead growth rate of the Lagrange multiplier, depends on the relative likelihood of the shock across agents. So if this is different, the Lagrange multipliers are either going to grow or going to shrink. So what happens when let us look at a path where lambda t goes to infinity. So on paths where lambda t is going to infinity, you have consumption of agent 2, which is, so agent 2 is going to dominate because lambda t is like the implied weight on agent 2. Since utility is bounded below, as consumption goes to 0, the gap in the continuation values also goes to 0. So for agent 1, the gap in the continuation values is essential for this probability twisting. It is the difference between the values across states which matters for how the agent goes from his approximating model to his worst case model. So as on paths where lambda t goes to infinity, agent 1's consumption is going to 0, and his worst case model is going to go towards his approximating model. But agent 2's worst case model is going to go towards something which is his approximating model twisted by the maximum or by the fact that he is now consuming the entire aggregate endowment. So I'm working with IID case. In the limit. So since we have an we have the IID shock, we can show that in the long run, the growth rate of the Lagrange multiplier approaches a constant, which is given by 3 terms. The first term is the relative entropy of agent 1's approximating model with the data generating process. The second term is a relative entropy of agent 2's approximating model with the data generating process. And the third term is the fact that the relevant beliefs which are going to affect the growth rate of the Lagrange multiplier have this extra term because agent 2 is now facing the entire aggregate risk. So if lambda t actually goes to infinity, we have a restriction that this sum of this g lambda infinity has to be greater than 0. We can do an equivalent computation for lambda t going to 0. And what we get here is that the necessary conditions for either agent to dominate is that the difference in the relative entropies is larger than some non-degenerate interval. So this is, at this point, we can compare the difference with Bloom and Easley, or when theta goes to infinity. So in that setting, any arbitrary difference between the reference model is sufficient and necessary for either of the agents to dominate. Here, what is happening is that since what matters is the worst case beliefs, even if the approximating models have a particular ranking with respect to the data generating process, that ranking can be switched when you go to the worst case models. And that is important here. For that ranking to switch, so if the approximating models are close by, then this ranking can actually switch, which means that the Bloom-Easley force will not work always in favor of one agent. And what it means, you could have survival. In terms of economics, what's happening is the following. Suppose the approximating models are close by but are different. As one of the agent is dominating and the other guy is going to 0, the way the exponential twisting is going to work is that the poor agent is going to be closer to his approximating model, and the rich agent is going to worry about the entire aggregate endowment. He's going to be more pessimistic. In terms of insurance arrangements, and here I mean the complete market assumption, he's going to buy more insurance in bad states. So the rich agent is going to over-insure himself in bad states by paying more to the poor agent in good states. So this is optimal for him because he overestimates the likelihood of bad states. And pessimism means that good times occur more often than the agent perceives. So typically what's happening here is that there is a wealth transfer from the rich agent to the poor agent, and that is helping him come out of this emissarization result. Now the poor agent is becoming rich. So you can apply the same argument, and then he's going to transfer money to the other agent. So agents are going to cycle in this wealth distribution. In some cases, we can show that this transition is degenerate in the limit, in the sense that there's going to be a particular wealth distribution that is going to remain constant. And that need not be half-half. It could depend. It could be anything. So here is a picture which would make the mechanism more clear. So there are two panels here. The first panel is for when agents fear model uncertainty, and the second panel is when agents do not fear model uncertainty. What I'm plotting on both these panels is the growth rate of the Lagrange multiplier. Now this growth rate depends on the shock. So there are two lines in each of these plots. So let me go to the first panel. The dotted line is the growth rate of the Lagrange multiplier when the aggregate endowment is high. So when V is low, or the promised value of agent 2 is low, which means that agent 2 is near emissarization, in good times, there is a positive drift to the Lagrange multiplier. So this is coming from the fact that he's benefiting from, so the other agent, the rich agent, is paying him more in good times for buying insurance against bad times. So the fact that you have a positive drift to, when agent 2's promised value is low, in good times you have a positive drift to the Lagrange multiplier, and in bad times you have a negative drift to the Lagrange multiplier. At some point, this thing is switched around. In fact, when we have two shocks, these two lines cross at some point. And at that point, the growth rate of the Lagrange multiplier is 0. So this statement is only true generically for two shocks. When you have more than two shocks, this may not be true. But what it means is that if you actually arrive at this point,
no. When you say two shocks, you mean?
Two shocks, Y high and Y low. Yeah. Two realizations, yeah. On the other hand, if you look at the growth rate of Lagrange multipliers when agents do not fear model uncertainty, we saw earlier that the growth rate of the Lagrange multiplier is just given by the differences in the likelihood of shocks. And if these likelihoods are exogenously different and do not adjust for the wealth, the Lagrange multiplier is either going to be positive or the growth rate of the Lagrange multiplier is going to be positive if certain shock occurs, or it's going to be negative if certain shock occurs. Yes, exactly. Which means that either multipliers will go to infinity or go to 0. So there is emissarization here, and there is no emissarization here. That is the message. Because there is an endogenous component which could switch around the identity of the agent who is farther away from the data generating process. So we saw in the earlier section that with symmetric information and asymmetric priors, when utilities had a lower bound, we had a particular heterogeneity in belief, which allowed survival for the poor agent. We needed the rich agent to be more pessimistic and give money to the poor agent or have, on average, a wealth transfer to the poor agent. Now we are going to have a case where we have symmetric priors and asymmetric information. To make matters simple and to focus what is the contribution of asymmetric information, I'm also going to keep the aggregate risk. I'm going to eliminate aggregate risk. So the key thing here is to make sure that insurance arrangements now have to satisfy incentive compatibility. Okay. The efficient allocations can still be described by the planner's problem, but we have to modify the planner's problem in a couple of ways. First, we are going to define the ex ante version of the planner's problem. So what is the utility of agent 1 before the shock is realized? Since the shock is private information, we need to have the assessment of utilities before the shock is realized. So V naught, which was in place of V, is now the ex ante promised value to agent 2. And the planner is choosing the following objects: consumption as a function of the report, and continuation values as a function of the report. These choices are such that this ex ante value to agent 2 is delivered. And secondly, this menu of choices, that is two values for consumption, one for state, one for each of the S shock, and two values for the continuation utilities, one for each of the S shock, have to satisfy incentive compatibility. And by incentive compatibility, it means that both of the agents in both of the states should have incentives to report the true shock. So these are further restrictions on the set of allocations which can be this can be interpreted as further restrictions on the planning problem to characterize the efficient allocations. So the incentive constraint work pretty much as you would expect them to work. So on the left-hand side, you have the value, ex post value of the agent from the plan which he would get if he reports the true state. And on the right-hand side, you have the value to the agent from the plan if he reports the other state, plus he'll have the difference in income, which he can run away with. So what am I doing here? This is like a Negeshi problem. I'm maximizing the utility of one agent with respect to the fact that I keep the promises to the other agent. Okay, so I'm not taking a stand on the beliefs of the planner. This is Pareto efficient. So I'm using the beliefs which are implied for each of these agents. So Q is agent 1's values, and V is agent 2's values. So think of the Lagrangian of this problem. So you'll have a weighted sum of these two values, and that is what the planner is maximizing. The important thing here is that those Lagrange weights are going to be state dependent, and they're going to change over time. But essentially what I'm solving is just a weighted average of values with respect to, and those values are computed with respect to the beliefs of the agents. Yeah. 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 So think of this. Okay. Think of this incentive constraint as further restrictions on the consumption space. Yeah, because the identity of the principal and who is the agent and who is the principal is not. I won't be talking about a decentralization here. Yeah. But I hope these incentives themselves are clear. Okay. Further, we have non-negativity bounds on consumption, and these come from the incentive constraint, and they ensuring that these bounds are satisfied means that consumption is positive even on off equilibrium paths, because we ex ante don't know which of these constraints are going to be slack and which of these constraints are going to be binding. But when we solve the problem, we have to make sure that along all paths, consumption is positive. What this means is that, so let's see the consumption of agent 1. when he gets a low income shock. That consumption can be at most y minus delta, and the consumption in the alternative state has to be at least delta y. Similarly, we can compute now the bounds for the continuation value. And these bounds are computed by looking at the worst possible consumption and the best possible consumption for the agent. And we have the promised value, or sorry, we have the value of that particular plan. And that bounds the choices for the continuation values. So having U0 well defined is good for this reason, that it makes the space compact. So before going into the entire dynamic problem and how the planner uses all the incentives or all the instruments to provide incentives, let's first look at a static case. So the static case is such that there is only one period of private information. So there are no continuation values. What this is going to mean is that the set of incentive constraints is going to boil down to a linear constraint on consumption. And this is intuitive. It says that the consumption for agent 1 in the high state has to be at least delta y more than the consumption which he would have in the low state, where delta y is the amount of income he can run away with. So since these incentive constraints are ex post in the static problem, the attitude towards uncertainty or model uncertainty do not appear in the shape of this consumption plan. In particular, you're going to have whether you have theta equal to infinity or theta less than infinity, you're going to have the difference in consumption to be a fixed number, delta y. So now, how do we compare the set of Pareto efficient allocations with and without model uncertainty? So we need to align them on a certain on a common ground. And we wrote up the problem where the state variable was continuation values. Now this necessarily is not comparable, because as you change state, sorry.
You may have a multiple equilibrium, right? Yes, because the principle is a value function in the constraint, right? It's not contraction, right? So you could have multiple equilibrium.
Yeah, but the computations which I do not have multiple equilibrium.
It's possible, I think.
Potentially possible. I actually don't have a proof for existence or uniqueness. So, yeah. Yeah, you're right. It's the constraint set is non-convex. It's not a contraction. Yeah. So how do we compare the contracts across these settings, theta equal to infinity and theta less than infinity, or when agents fear model uncertainty and agents do not fear model uncertainty? So we can one choice is that we can align them on the Lagrange multipliers. So given the Lagrange multipliers, a value for the Lagrange multiplier, we can figure out what is the consumption plan that would be given in the case where theta is equal to infinity, and what would be the consumption plan which would be given when theta is less than infinity. So what this proposition says is that there is a particular twist to the set of optimal plans, and the twist goes as follows. When lambda is large enough, or when the consumption of agent 2, lambda is again always the implied Pareto weight on agent 2. So when lambda is large enough, or when the consumption of agent 2 is higher, the corresponding contract, when theta is less than infinity, gives larger or higher consumption to agent 1 than what he would get when theta is equal to infinity. So this is something which is slightly different than what we saw in the complete markets example. Here, the guy who has low consumption is being favored in bad times. On the other hand, when lambda is low enough, you have the reverse situation, that the consumption for agent 1 is lower than what you would get if theta is equal to infinity. So what is happening here? This particular twist for the consumption plan comes from the fact that there is an interaction between heterogeneity in beliefs and the shape of the consumption plan, which is pinned down by the incentive constraints. So first, we know that the difference in consumption is always equal to delta, and that was true irrespective of attitude towards ambiguity. As lambda becomes larger, consumption of agent 1 diminishes because the Pareto weight of agent 2 is becoming higher. Now these guys are facing a lottery which is C plus delta and C. When C is high, the spread in values which comes from C plus delta and C is much smaller. And the spread in values which comes from, let's say, 0 and delta as compared to y minus delta and delta is much larger, which means that the guy who has low consumption is going to relatively overestimate the state in which he has low income. Well, what that means is that now the efficiency force, which says that you have to allocate more consumption to the agent who considers that state more likely, would mean that everything else being equal, you want to give a little bit more consumption to the agent who perceives that state more likely, and here it would be the guy who has low consumption. So which means that as lambda goes to infinity, the contract is twisted in a way that agent 1's consumption in low state is higher than what he would get when lambda is going to infinity. So now when we go to the entire dynamic case, the planner actually has two choices. He can vary consumption across state, which was the variation in the consumption menu, or he could vary consumption across time, which comes from the variation in the continuation values. And typically, he'll use both these instruments to provide incentives. So we can always use the sequence of simple contracts which we had earlier, which kept the difference in consumption to be delta. Now these contracts are incentive feasible, as we saw, because the continuation values do not change. The incentive constraint boil down to the static incentive constraints. The thing here is that when the ex ante continuation value is either at the extreme, these contracts are optimal. And by optimal, and since they're optimal there, what it means is that if you start from either of these values, you get the static contract and you get the same continuation values, which means they're also absorbing. So if you ever reach either V0 or Vmax, you're going to remain there, and you're going to repeat the same set of you're going to repeat the static simple contract again and again. So obviously, these are not optimal in the interior, and the planner can do much more. So now let's see what are the properties of the optimal contract when you allow the planner to give or to smooth consumption across both these instruments. Let me denote delta C by the difference in consumption for agent 1 when S is high and S is low. So the optimal contract will have the property that this difference is less than or equal to delta, and this difference, so which means that there's going to be more insurance across states, and to keep the incentives right, is going to vary continuation values. So this is going to be true, and at the edges, these are going to hold with equality. So you have the absorbing contracts. Now the incentive and the feasibility constraints are going to, or typically, partition the state space in the following way. So remember, we had two sets of inequality constraints. One were the incentive constraints, and the second were the bounds on the consumption. So as we go from Vmin to Vmax, or as we go from low values of promised utility to agent 1 to high values of promised utility to agent 2, we pass through the following regions. So in the first region, where agent 1's promised utility is low, the upper bound on agent 1's consumption is binding. Also, what is binding is his incentive constraint in the states when he is rich. So typically what happens is that the incentive constraint for the agent who has higher consumption is binding in the state where he has high income. What it's going to mean is that after a certain point, you will have the incentive constraint for agent 2 binding in the state when he when he has higher income, which is S low. And in the first part, you have the incentive constraints for agent 1 binding. There is a region in the interior where both these incentive constraints bind. And across at the extreme end of the state space, we have the lower bounds on the consumption being binding. So now, what is the interaction between heterogeneous beliefs and incentives in this setup? So take a low value of V naught. The first order conditions with respect to V star will have the following form. So you have the Lagrange multiplier if the state was S low, and the Lagrange multiplier, the corresponding Lagrange multiplier when the state was S high. So if mu1 and if mu1 was 0, this boils down to the standard complete market conditions, which says that the growth rate of the Lagrange multiplier is going to be related to the relative likelihood of the shocks. Since you have the incentive constraint on the rich guy, which is agent 1, is binding, this first order conditions would imply that continuation values have to spread. And this is the insight from Atkinson and Lucas, that you have to spread continuation values to provide incentives, and you want to do it always, which means that lambda S low would be larger and lambda S high would be lower. What it means is that eventually, after a sequence of S low or S high shocks, you would go to either V min or V max, and you would have emissarization. Now there are two motives for varying continuation utilities or continuation values. One, you want to change them for incentives. But the second one, you want to change them because agents have heterogeneous beliefs. These heterogeneous beliefs arise because of the fact that some uninsurable risk is going to be borne by the agents. We have asymmetric information, so there is going to be some uninsurable risk, which means that agents are going to have attitudes, or agents are going to distort their reference models. Now, if this relative difference in beliefs goes in the right direction, we might have a survival force which would prevent these Lagrange multipliers going to either one of the ends due to this incentive constraint. So what would be helpful if we have the likelihood of the probability which agent 2 puts on the states when he has low income to be much higher than the likelihood which agent 1 puts on the states when he has when he has high income, when V is low. So we saw earlier, the earlier logic said that the poor agent overestimates the states when he has low income. So this holds here also. So these are the distorted, or these are the worst case models for both the agents. The red lines are agent 2 and the black lines are agent 1. The dotted lines are the probabilities for the low income states for each of this agent, and the black lines are the probabilities for the high income state. So what we see here is that relative pessimism is declining in wealth because of the concavity, which means that in terms of our first order conditions, agent 2, who is poor and has low income in state S high, is going to overestimate the probabilities for that state, and the reverse is going to hold for agent 1. This means that now lambda H is not going to be as low as what it would have been just for incentives. So if you plot the policies from this setting, we have the following picture. So the upper panel is corresponding to Atkinson and Lucas, where theta is equal to infinity, and this is how the continuation values move. So this is the change in the continuation values as a function of the continuation values. You see that this is pretty symmetric in the sense that if one state happens, the continuation values move left, and if the other state happens, the continuation values move right. With enough shocks of either, shocks of one direction, you're going to be pushed into the boundaries, and you're going to stay there because of the absorbing nature of the contracts at the boundary. Now, as we argued in the earlier section, you have this feature where agent 2 really cares about the states when he has low income, which means that this fall in the continuation values when you have the shock S high would be much lower. If you have enough ambiguity, or if theta is low enough, this will provide a positive drift to the continuation values in this state, and this is going to push the continuation values in the interior, which means that typically you will have the survival force, which is going to push poor agents into, or which will push the guy who is on the verge of extinction into an interior region. So these are a couple of plots. So what I'm plotting here is conditional on, this is the exit behavior. So what I'm doing is the following. Take an initial promised value and draw multiple samples of sample paths of really long duration and see what happens on those paths. So, and then what I'm plotting is the fraction of paths on which agent 1 or agent 2 exited on either of the boundaries. So with expected, or with theta equal to infinity, you have that either of the agent, so you have the hazard of exiting strictly positive and diminishing, because on the left you exit on the left side where agent 2 is emissarized, and on the right you exit on the other side where agent 1 is emissarized. When theta is less than infinity, this practically does not happen unless I really start very close to the boundary. These are the ergodic distributions for consumption and for continuation values. We see that because of the emissarization with theta equal to infinity, you have a 2-point distribution, and when theta is less than infinity, the push which forced continuation values in the interior gave a nice continuous distribution in the unconstrained region. These are typical sample paths. The black line is the sample path of consumption for agent 1 from different starting values, and the red line is the path for agent 2. I'm just done. And we see that it either goes to 0 delta, or it either goes to y minus delta delta. So what we saw here was, so let me conclude. So what we saw here was that endogenous heterogeneity of beliefs generated survival forces in these two alternative settings. And the heterogeneity was very different when we had aggregate shocks and when we had the unobservable idiosyncratic shock. In the first case, we had that richer agents who took most of the aggregate endowment were more pessimistic. On the other hand, in the allocative shock, we saw that concavity of the utility function, the guys who had low consumption but had a fixed difference in consumption, overestimated, or they were more pessimistic. They overestimated their low income state. Both of these, or the heterogeneity worked in the right way in both of these examples to generate survival. And so as an extension, I study cases where you have uncertainty about parameters. I'm going to skip the results because I don't think, yeah. So let me come back to your question, how the survival in Bloom and Easley is different from, or is related to Anderson. So Anderson studied a case where you had symmetric priors, but you had heterogeneity in thetas. So what is necessary? And now what I'm doing is I'm changing the heterogeneity from the theta parameters to the priors. Okay. Now let me tell you why the survival could be different. So let us take an example. So the key thing in Anderson's result is that the survival is always degenerate. You either have a stable point, so you always have the asymptotic survival as a point where the consumption shares are either half. So depending on theta are constant. They could either be the extremes if there is no stable well distribution, or there could be an interior solution, but it is always degenerate. And here I can give you an example where asymmetry in priors need not necessarily have degenerate distribution. So take a case where either the idiosyncratic risk is 0. So we are in the Bloom and Easley case. So in general, assume either the idiosyncratic risk is 0 or agents only disagree on the values of the aggregate shock, which takes 2 values. Pick alpha between 0 and 1. Okay? You can compute values for agent 2 and agent 1 at a constant, at a consumption plan which gives alpha to agent 1 and 1 minus alpha to agent 2. Okay? Using the values, which would just depend on the primitives now, and alpha, you can compute the distorted probabilities for agent 1 and agent 2. Plug them into the growth rate of the Lagrange multiplier and compare the likelihood of these shocks for YH and Y low. So you'll have one value for, so this is the distorted, there should be a tilde here. This likelihood for, this is the likelihood for the shock YH, and this is the likelihood for shocks Y low. So if this difference is 0, we'll have degenerate survival, in the sense that they guess that there is some alpha such that the worst case probabilities are same for both the agents. Would mean that, and if these growth rates are equalized across states, you would have a constant lambda, which would be independent of y, and also the data generating process, such that once you reach there, you'll always remain there, in the sense of Anderson. Now note that if you had 3 shocks, you could satisfy a particular alpha for the 2 of the shocks, and you can generically have a third shock in such a way that you won't satisfy it. So in particular, you won't have degenerate survival when you have asymmetric priors. Thanks.